We're going to start chapter 35 by seeing what do we mean by a system of differential equations. I'm hoping you remember from college algebra seeing things like this. Here we have a system of equations involving two variables, x and y. We learned in college algebra two ways of solving that. Actually, we probably learned more ways, but these are the primary two ways and the two that we'll be using mostly in differential equations. So first off, let me show you about the elimination method. To do the elimination method, all we need to do is to adjust the coefficients of one of the variables so that they match. For example, here I'm going to make the coefficients of y match by multiplying the first equation by 2 and multiplying the second equation by 3. That gives us matching coefficients, opposite in sign, which we can now add the two equations together. Hence the y's subtract out. That's where it gets the name elimination. We can finish solving that equation and then substitute that back into either equation to come up with the other variable. So that's the elimination method. The Gauss-Jordan method uses what's called an augmented matrix. And again, if you haven't done this before, see me in class and we'll go through it in more detail. But you can see how the augmented matrix is created using the system of equations. Of course, this is contingent upon our system of equations being in standard form. X, y equals constant. They have to both be in that form. And we can solve this using our calculator. That's what makes the Gauss-Jordan method quite useful. On the TI-89, we have a command. By the way, we also have this on all the TI graphing calculators, but there's a command called RREF, which stands for Reduced Row Echelon Form. As you can see in this matrix, reduced row echelon form means that we have ones in the main diagonal and zeros in all of the other spots in the square of the matrix. If that's the case, these are the answers for the two variables in the order in which they appear. Now here's a typical system of differential equations. Now these are referred to as linear differential equations. Hopefully you remember from way back in chapter 1 why. And we have the first derivative of each of the two functions and the functions themselves. Now notice that we are using t as our independent variable so that we can use x's and y's as our functions, because we kind of like x's and y's when we're doing systems of equations. Now again, this is immaterial what variables we use, as long as we understand what we have here is two functions. We're calling these two functions x and y, and one variable, which is t, one independent variable. And so here's a system of linear first order differential equations. Now typically what we do is we just understand that, okay, we're using t as the independent variable, and we take all the t's out. Now, this is a little nicer looking, a little bit more compact, a little easier to write when we're having to work all of this out. And again, we're working under the assumption that we know there's a t involved here, even though it's not explicitly written. Now, one of the things I mentioned earlier was that it doesn't really matter what we call the variables. Here, I've taken that same system of equations where t is the independent variable, only for the two functions, instead of calling them x and y, I'm calling them x number 1 and x number 2. This is real common when we're doing linear equations, because as the linear equations grow and we get more variables, if we were to use x and y for two variables, that works out pretty good. If we had three variables, I guess x, y, and z would work out pretty good. If we had four variables, what would we use after z? Like x, y, z, and so oftentimes we use numbers for our variables. We just use x number 1, x number 2, and just kind of number the variables. Now, the first thing we need to do with the system of equations is to make sure what we know about checking solutions when we have a system of equations. Well, we did this again way back in chapter 1. We need to take the first equation and check to see if these two x's and y's are solutions to that. So if we start with the first answer that we're claiming is a solution, we want to do its derivative to get x prime. Then we want to substitute that, x and y, and then simplify. And of course, since these are identical, that means that these are solutions to the first equation. Now, before we can say that this is a solution to the entire system of equations, we need to make sure it fits the other equation. So we take the other equation and do the same thing. We take the y solution, do its derivative, plug in the x and the y, simplify, and see if they're the same. Since this is also a solution, then we say that that is a solution.